Right, so in today's lesson we are looking at a segment of electricity and magnetism, and so we decided to start it from scratch, from the first part, so that we actually build up on something. And so under electricity and magnetism we are looking at three main components. That is electrostatics, we are also looking at current electricity, and then lastly we are looking at a part of magnetism. And so these are the main areas that we'll be looking at as we are dealing with electricity and magnetism. And so some of the key components that we must be considerate about as we're looking at this course is that this is a branch of physics that actually deals with charges at rest. Electrostatics in this case as the first component, electrostatics. So this is a branch of physics that deals with charges at rest, and we need to note that a charge is simply a fundamental quantity of a unit substance. So any substance is going to have a charge, and basically we have two types of charges. We have what we are regarding as a positive charge, and what we are regarding as a negative charge. From there, we need to note that we have laws of electrostatics. We'll just get a new slide. Laws of electrostatics. And so under laws of electrostatics we are actually finding something that is actually very familiar with us, and the concept is that of repulsion and attraction. And so these two are regarded as a force. There is a force of repulsion, that is a force that actually pushes two things away from each other, and then there's a force of attraction. This is simply a force that actually brings two or more particles together. And so under the law of electrostatics we are actually finding that this law of electrostatics states that like charges repel, and unlike charges attract. And so what we are simply saying is that if we have two charges, one is positive, the other one is also positive, because the charges are the same, there's going to be repulsion, meaning that they will move away from each other. It will simply be the same thing even if we have both as negative charges, we'll still have a repulsive force. So repulsion is going to take place. On the other hand, if we have different charges, If one of them is positive, then the other one is negative, then there's going to be an attractive force. Attractive force, or force of attraction. If this is negative and that is positive, we still have, so they'll move towards each other. Force of attraction. And so it is very important to note that the repulsion or the attraction is or can be calculated. We are able to find the magnitude of this force that is actually bringing these particles together or moving them away. And because there's going to be an aspect of movement where we're saying moving towards each other or moving away, meaning that there's direction that is involved, and so that qualifies for it to be a vector quantity. And so the force that we have talked about can be calculated, and that is what we'll be regarding as electric force. And so we are saying the electric force will be denoted by F with a small e down there. This actually represents the electric force. When we see that, we are simply talking about the electric force. And by understanding of force, meaning that it is measured in newtons, the SI unit is newtons. Newtons, like that. So there is a scientist that actually established a relationship that is there between two charges that are separated by a particular distance in relation to the electric force. And so in his research, he came up with what is known as the Coulomb's law. And so it is very important for us to actually be able to state the Coulomb's law of electrostatics. I want to believe that this the Coulomb's law, where we talk of voltage is equal to the product of current and resistance, but we are going to be specific and say the Coulomb's law of electrostatics. And so this states that the force between two charged particles is directly proportional to the magnitude of the product of the charges and inversely proportional to the square distance. So we are saying that this force between two charges is directly proportional to the magnitude of the product of the charges and inversely proportional to the square distance. And so you observe that what we have stated can be written mathematically because we have weights like directly proportional. So there's direct proportionality, there's weights like magnitude, there's product, there's inverse proportionality. And so we are then saying that this force, which is a vector, is simply is directly proportional to the magnitude of the product of two the same force is inversely proportional to the square distance. And so combining these two, we are able to then say that this force is directly proportional to the product Q1, Q2 over R squared. And so once we have this, when we change the proportionality sign to an equal sign, we introduce what we will be calling the constant, the proportionality constant. And so Q1, Q2 over R squared. And so the K that we have, this K there, where K is the Coulomb's constant. We are regarding this as the Coulomb's constant, and is given by 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. So epsilon naught, this is what we are regarding to as the permittivity of free space, and is given by, it's actually a value that is 8.85 times 10 to the power negative 12 times 10 to the power negative 12 Newton meter squared. We have that Newton meter squared per Coulomb squared. And so when this value is replaced in this notation, then K can be evaluated. And so the value for K that we'll be considering in this case, after we have evaluated our K, will simply be 8.99 times 10 to the power 9. And so with the units, it's just going to be the reciprocal of the units for the permittivity of free space. And so since we had let's see, so the units for permittivity of free space is actually Coulomb squared per Newton. Let me just erase that. Okay, so we are saying this is going to be Coulomb squared per Newton meter squared, like that. And so once we have that, then we are saying that the value for K is simply the reciprocal, and so it's going to be Newton meter squared per Coulomb squared. And so this is the value, or at times we'll actually simply be saying K is equal to 9 times 10 to the power 9 Newton meter squared per Coulomb squared. So we are simply saying that the force is simply equal to K Q1 Q2 magnitude over the square distance. And so this is, in summary, the Coulomb's law. Furthermore, we have two important things that we need to take note when we are doing our calculations in order for us to determine the electric force between two charges. And so if we have two charges and they are of the same charge, we are saying that the force that is here is a repulsive force from the laws of electrostatic repulsive force. And so if we have two charges that have got different charges, for example, that is positive, that is negative, here we are saying that we have an attractive force. And so as we are doing our calculations in order for us to determine the electric field, we are simply saying that number one, for like charges, we have a repulsive force. Like charges, we have a repulsive force, and all repulsive force are negative. So if we do our calculations, if we have Q1 is a positive charge, Q2 is a positive charge, then the answer that we are getting, the electric force that is between the two charges, because they are like charges, is going to be negative. On the other hand, the second point is that for unlike charges, we have attractive forces, attractive force, and so all attractive forces are positive. And so I'll pause a bit so that we have a session of examples. Once we are done with the examples, then we'll have some work that we'll be able to work on.